Hey guys, it's Mrs. Winger. Welcome to my channel. I'm glad you found the video okay. Today we're going to be reviewing section 6.1 and 6.2 to get us started in our chapter 6 review kickoff for this week. And let's just jump right in and get started. Chapter 6, as you may remember, was all about exponential growth and decay. So let me just remind you just kind of what that function looks like. This is the general format for both exponential growth and decay functions. Y equals a b to the x power. To determine if it was growth or decay, we look at the value of b right here, which is the number that the exponent x is attached to. If b is greater than 1, so maybe something like 5, then this would be an exponential growth model, and on a graph it would look something like that, where it goes up, going from left to right. If b is in between 0 and 1, so maybe a number like 1/2 or a decimal like 0.8 or anything like that that's in between 0 and 1, then this would represent exponential decay, and that would go down from left to right when you look at the graph. Now, in both exponential growth or decay, this number right here, a, is just any number that's greater than 0. So in both exponential growth or decay, I could write a function that has some positive a value like 5. And something like this would represent exponential growth. And similarly, something like this still having an a value of 5, but this time if I change the b value to be something in between 0 and 1, this would represent an exponential decay. And if you were to graph each of those on a graphing calculator, you would see that this one looks like this, and the bottom one would look like this, even though they both have an a value that's positive. Now, something I want to point out that was really helpful when we got to graphing these a lot is we saw a lot of examples where this a value right here was 1, or it just didn't look like there was an a value. Like over here, I'm going to write an exponential growth function that looks like this. It might look like we don't have an a value, although we technically do. It's just an invisible 1. So you can imagine a 1 times right in front of that 5 to the x, and then you see that a is actually the number 1. So when we would have functions like this where it appeared like there wasn't an a value, although we knew it was 1, it always went through the point 0, 1, both on exponential growth and on exponential decay. So I'm going to mark that point in. And let's think about why that is. If I look at this point right here, that y-intercept, the x value there is 0. And so if I think about coming back up to this function and plugging in 0 for x, remember as an exponent rule that anything to the 0 power is 1, which makes sense why the y value at that point would be 1. So that was a common anchor point that we used to graph exponential growth and exponential decay models when we saw these models where the a value was 1, which is a really typical model. All right, so let's practice graphing a few of these. I think both of these examples would be pretty easy ones that you could do without a calculator, and I would expect you to be able to do some quick calculations. So before we jump into plotting points, let's determine which one is an exponential growth or which one is an exponential decay. Remember, what we're looking for there is a b value either greater than 1 or in between 0 and 1. So this first example, the exponent x is attached to 2, so that means 2 is the b value. Since 2 is greater than 1, that means that this is going to represent an exponential growth model. For part B, the x is attached to 1/2, and since 1/2 is a number in between 0 and 1, we know this is going to represent an exponential decay model. So that part's done. So now let's go ahead and plug in our points so we can get this plotted. Since neither one of these are weird numbers or like weird decimals or anything like that, I think for both of them we can go ahead and plug in just typical easy values for x like 0, 1, 2, and then a couple negatives to get the other side of the graph, maybe like -1 and -2. So I'm going to take a second, pause the video, and fill in those values for those just typical easy x values. All right, so a couple things to remember here for me to calculate what the y value is going to be based off of these easy x values that I plugged in. We have an a value of 1. There's no coefficient right here in front of it. And so if I think about plugging in 0 for x, that's just going to be a simple 2 to the 0 power, and we know anything to the 0 power is 1. So that's kind of a nice one to get us kick-started, and we already know where the y-intercept is going to be. In fact, if I look over at part B, I could fill out the exact same thing right now. Even though one of them is exponential growth and one of them is exponential decay, since they both have an a value of 1, they're having the exact same y-intercept because anything to the 0 power is 1, which really drives that point home. No pun intended. Okay, so let's keep adding in some y values for these x values using just some simple calculations, like if I want to fill out when x is 1, 2 to the first power is just going to be 2. Similarly, 2 to the second power is going to be 4. And let's just do a quick recap on what do we do with these negatives, like 2 to the negative 1. Remember that you can make an exponent positive by flipping it to the other side of the fraction. So this is going to be 1 over 2 to the positive first, which is just the same thing as 1/2. Okay, similarly when x is negative 2, so let's do this one now. When x is negative 2, then we can write the function as 2 to the negative 2, making that exponent positive by moving it down to the denominator. So 1 over 2 squared is the exact same thing as 1/4. Alright, so that's how I calculated these points. I'm going to take a second now and just plot these points and connect the dots. Alright, so I plotted my points, I connected the dots. Notice that when I read this graph going from left to right, it is going up exponentially, which really drives the point home that this was in fact exponential growth. Other things to point out is, again, our y-intercept is at 0, 1, and this graph has an asymptote on the negative part of the x-axis over here. Okay, so let's go ahead and do exponential decay in part B and fill in these values for the x values that I already have the chart filled out for. So I would take a second right now and pause the video and fill out those y values on your own and graph it and just see if you can get a nice looking pretty exponential decay. Alright, so there's what my graph looks like. Again, noticing the y-intercept at 0, 1 and noticing that it has an asymptote at the positive part of the x-axis over here. When I read this graph going from left to right, the graph is going down, which again makes sense because we already knew that it was going to be an exponential decay. Okay, so since I had you guys try that last one on your own, I'm not going to have you graph these ones. I just put these on here because I want to make sure that we understand that it's okay when we see decimals, and I think a lot of times when we see decimals like this or maybe like this, we just automatically assume it's going to be exponential decay because we think that decay might just be anything with a decimal. Which is false. That's not accurate. So again, think about our definition. Exponential growth is a b value that's greater than 1. So which of these, the first one or the second one, has a value greater than 1? And hopefully you're answering that in your head that the second one. That b value is 1.5. Yes, it's a decimal, but it's greater than 1, which means this is exponential growth. And if I were to take the time to graph it, it would go up like that. Now, of course, that is not perfectly drawn by any means and totally has the wrong y-intercept, but you get the idea that it would go up like that. If I were to take the time to graph this first one over here, I would expect that to be going down because the b value is 0.25, which is 1/4 as a fraction, and that would definitely be an exponential decay. All right. Awesome. So let's move on from graphing and look at our next topic, which is using models to represent real-life situations. All right, so this is an example where we have a function describing to us the dollar amount of a car after a certain amount of years. So what is the value of this car maybe 10 years down the road? So first things first, I just want to figure out, is this telling me a function that is exponential growth or exponential decay? Well, to answer that question, I'm always looking for the b value, which is right here. It is the number attached with the exponent. It's the base of the exponent. 25 has nothing to do with if it's exponential growth or decay. The only number that matters with answering that question is this one right here, which is 0.85. Is 0.85 less than 1? Yes. So this particular model represents exponential decay, and that's my answer for part A. So when I try and figure out what is the annual increase or decrease, what I always like to think about is if I start from 100%, is my number getting bigger or getting smaller? So if I think about a car's value, 100% of its value would just represent the car value staying the exact same. So is 0.85 bigger or less than 100%? Well, it's less, and we already answered that because we already said that it's less than 1. And 1 as a percentage is 100. So we already know that 0.85 is representing a decay, something less than 1. But how much less than 1? If we start at 100%, what do I have to subtract off to get to 85%, the number that's given to us in this model? So think about that. 100 minus what number is 85%? Hopefully in your head you are thinking, oh, that's 15. And that's exactly right. If we see a B value of 0.85, you can think about it as starting from 100%, we took off 15%, which left us with this 0.85. And so that tells me that it was a decrease of 15%. Okay, now let's contrast that with something. I'm going to draw a quick example up at the top of the page, and let's contrast that with just a random different example I want to give you guys to show you another type. So up at the top, I've drawn an exponential function. I know it's exponential growth because this B value here is greater than 1. So if this were a word problem where it asked me to identify the annual percent increase or decrease, I would say, okay, how much greater is this number than the number 1? 1 representing 100%. So 1 plus what gives me? 1 plus question mark gives me 1.17. And what's the answer to that equation? If it helps you guys to kind of fill that in as an x and actually solve this out like you would in Algebra 1, you would get that the answer is 0.17, which represents 17%. This time we would say increase since this number up here was greater than 1. Alright, so let me remind you now the formula for compound interest looks like this. Remember that if something is compounded annually, like the examples we just finished doing, then n would be 1 because n represents the amount of times it's compounded per year. So if it's compounded annually, that means it's only compounded once per year. Let's see what this formula looks like when I plug in a 1 for n. So imagine there's a 1 for n. What does that do? Well, this term right here, r divided by 1, is just going to be r, and this term right here, 1 times t, is just going to be t. Let me write that out at the top. So when I plugged in n is 1, and simplified what that is, I got what I just wrote in blue, which is exactly your formula that we used for the last one, just for regular word problems where it gives you the fact that it's compounded annually. So compounded annually, you can think plug in 1 for n, and you will get what is in blue. If it gives you something else like quarterly, quarterly means you would plug in 4 for n. If it gives you something like monthly, then you would plug in 12 for n because 12 times in a year would represent monthly. Alright, so let's just identify what number will go to each letter. So if you deposit $9,000 in an account, that's P, that's the principal amount that you're starting with. If it pays 1.46% annual interest, that's going to be R as a decimal. Notice up here it says as a decimal. Let's just right now convert that to a decimal. Okay, and then I'm wondering what is the balance after 3 years? Years would be T, my time, so T is going to be 3. And we already talked about that if it's compounded quarterly, that means that N is going to be 4. So now that I've identified what each number represents in the equation, let's go ahead and fill out the equation with those plugged in numbers. Okay, so I filled in the equation. Notice this, before I type that on my calculator, I would just convert that to 12 or calculate it as 12. That way you're not typing in quite as much. Just be careful you are following orders of operation and check that you're getting an answer that looks like this. Since we're working with dollars, it only makes sense to round it to 2 decimal places, and problems like this probably will never tell you to round to 2 decimal places. It will just assume that you know that because we're working with dollars. All right, so let's jump over to start reviewing the natural base e. Remember that the number e is roughly 2.7. So that'll help us when we start to graph, just to remember what number that is and how it will affect what our graphs look like. These first couple examples, we're just going to practice regular exponent rules using a base of e. Just because we have a base that is a decimal does not mean we have new exponent rules. It is still the exact same exponent rules that we've been using all year and that you learned in Algebra 1. So let's start with the first one. I have the exact same bases. They both have a base of e, and in the middle they are being multiplied. So my product rule would tell me that I need to add these exponents together, which would result in e to the 11th power. Since e is an irrational number, I would not want you to plug that in and give me some rounded decimal, and that would be a huge decimal, by the way. I would just want you to leave it just like that. That would be the exact form. Okay, let's look at number 2. I have some things, they're being divided. I'm noticing right off the bat that these are both just regular numbers, so I can just divide those in the regular way that I normally would. So 16 divided by 4 is just the number 4. I can write 4 over 1 if I want, but there's really no need, and I like to just leave that part off to keep it as simplified as possible. And then let's look at these e's. I have 5 on the top and 4 on the bottom. Remember your exponent rule when you have the exact same bases like we do here. They both have a base of e, so I can subtract the exponents going in the order top minus bottom, which would be 5 minus 4 with those exponents, which is 1. So that leaves me with e to the first power. Again, there's really no need to write a first power, so I'm actually going to leave that part off. I didn't have a denominator, or you could think about as like you had a denominator of 1. No need to write it, and so that's my final answer of just 4e. Okay, with the next one, when you have an exponent on the outside, remember that it gets distributed, you can think, to every single term inside the parentheses. And when I say distributed, I mean it's getting multiplied to the current exponent. So if we look at the number 10, what's the current exponent on 10? It's not 0, because we know anything to the 0 power is 1. So 10 is not the number 1, therefore it must have not had an exponent of 0. We know it's actually an exponent of 1. So that's kind of good to consider when you think about multiplying that 3 in, that for the term that says 10, the exponent's going to be 1 times 3, which is 3. For the one that has a base of e, it is no worry that there's a variable in the exponent right here. You're still just going to do the exact same thing and multiply it. Negative 3x times 3 is negative 9x. Now, this almost looks good. The only thing that looks rough is that I have a negative exponent right here. Remember, we don't ever leave things with negative exponents, so I'm going to simplify that and make it a positive exponent by moving it down to the denominator. Okay, so let me write that out. Notice when I wrote that out, I also simplified 10 cubed as 1,000 instead of leaving it as 10 cubed. So that's my final answer. I can't take it any further, and I've done all my exponent rules. At this point, I'm going to have you guys pause the video and try the bottom 3 on your own. They mirror pretty much exactly the ones right above it, just with some different numbers. You can give it a try and just make sure you guys are getting the hang of it. So pause it here, hit play when you're ready to check your answers. Okay, so here are my answers, so you can quickly touch base and just make sure you guys got the hang of it. Again, the one that kind of involves the most rules is probably the last one, since I had to distribute the exponent of 2 to both of these. And 3 squared is 9, and then this e to the negative 4x. Once I multiplied it, I still had a negative exponent, which is why I moved it down to the denominator to make that 8x positive. Alright, so let's move on to very similar thing as before, determining if our function is exponential growth or exponential decay. Just because we're working with a base of e does not mean our definition of exponential growth or decay has changed. Again, I'm looking for a b value that's either greater than 1 or in between 0 and 1. So what's my b value? Let's look at part A. What number is the x attached to? Is it attached to the 3? Is it attached to the e? or is it attached to both? The answer is it is just attached to the e. If it was attached to both, it would have been written like this, and it was not. Oop, I did not mean to write an x there. I meant to write an e there. And it's not written like that. And so the exponent is just attached to the e. Again, think about e is roughly the number 2.7. Is that bigger than 1? Yes. And so this function right here represents exponential growth because the b value is e, which is greater than 1. So this is exponential growth. Okay, in part B, what's kind of hard to tell right now is we don't have an x, we have negative 0.5x. So I can't just look at it really quickly and decide if it's growth or decay because this is not in the form y equals a b to the x. It's negative 0.5x, so that's not that standard form. So what I first want to do is convert it to that standard form. So first thing I would do is say, okay, I have a negative exponent. Let's make it positive by moving it to the denominator, which I did over here. And now I want that x to sort of be on the outside. That way I can evaluate what the b value is, what the base is. So let me rewrite it now like this. What if I were to put the x on the outside of that whole thing? Is this line right here and this line right here, do they say the same thing? Are those equivalent statements? Well, let's just double check. If I were to see this problem for the first time, my natural instinct would probably be to distribute this x to both top and bottom. 1 to the x power, 1 to any power is still just going to be 1. So 1 to the x power is still 1. So this and this is equivalent. How about e to the 0.5? And if I bring this x in, will that equal this? Yes, it will. So now I can just look at the bottom square, which let me just clean that up a little bit and say that what I have in this blue square is the exact same thing as what's printed up here in the original question. So now I really just have to look at this part and say, is that funky looking thing bigger than 1 or in between 0 and 1? So if you type that in, if you type in on your calculator 1 over e to the 0.5, you get a number like 0.6-ish, which is in between 0 and 1. And so then I know this is going to be an exponential decay. So really the shortcut here is whenever you see a negative exponent attached with that x, flip it and make the fraction, or make it a fraction with a positive exponent and evaluate that number. So it's going to be the reciprocal and just see if that's going to be something that's greater than 1 or less than 1. Alright, so I'm going to clean up my screen here and let's just plug in some numbers for x for part A. Just looking at it right now, since there is nothing, no decimal or fraction or anything with the x, I can just go ahead and plug in my standard 0, 1, 2, -1, -2 values for x and see what that gives me. I'm obviously going to need to use a calculator for this since I'm working with a base of e and I doubt anyone knows those values in their head. But one that I can get really easy in my head is this one right here when the x value is 0. Remember when x is 0, anything to the 0 power is 1, which means that this part of it right here, e to the 0 is 1. So what's left is just 3 times 1, which we know is 3. So notice my y-intercept is not at 0, 1 this time, but it's at 0, 3. Alright, so for the rest of these, by the way, I'm not plugging in x equals 2 because this is going to get actually pretty large and go off my graph. So I decided to cut it off, having x equals 1 be my highest value. So go ahead and plug those into your calculator and see what sort of numbers you get, and then we'll plot those points. Okay, I know these numbers are kind of sloppy. I'm writing with my finger here, but for -2, I got 0.41, so that's roughly about right there-ish. For -1, I got 1.1, so about there. 0, I got 3, I already plotted that, and for 1, I got 8.5, which is maybe around there, kind of off my graph. So when I connect my dots, I can see that this is going up, which makes sense because we had already identified this as an exponential growth, but now just kind of verifies that what we said was true. And I can see here how the y-intercept changes when I have an a value out here that is different than 1. Okay, for my next one, let's go ahead and plug in points. I'll pause the video in a second and have you guys calculate the y values, but I do want to look ahead and maybe just plug in some smarter points for this one. Obviously, plugging in an x value of 0 is a pretty easy one, so I'll still want to do that. But since I'm going to be multiplying it by a half, actually negative a half, it might be easier to do numbers that actually divide by 2 evenly instead of having to deal with decimals. Like, for instance, if x is 3, then I'm going to have to do 0.5 times 3, which is just kind of annoying to deal with. So I think I'm going to stick with even numbers for this one. So I'm going to choose to plug in 0, 2, 4 if it doesn't go too far off the graph, and negative 2 and negative 4. All right, so plug in those x values, pause the video here, and see what you get for your y values. All right, so I figured out what those numbers were, generally rounded 2 decimal places. I didn't fill in one for 4 just because I was running out of space to write, honestly, with my finger, and that's the only reason why I didn't do it. So I plotted these points in green. I'm going to go ahead and connect them. I can see that it is forming an exponential decay model, which does make sense with what we said about the b value being, I believe that was like around 0.6, which is less than 1. And so that does make sense. That checks out with what we had predicted. Again, just kind of noticing the asymptotes here as we get into further graphing later on. Last slide for today is applying E, that natural base, to some word problems. And so we all love and know this formula, PERT, for anything that's compounded continuously. So unlike the last problems I showed you where it was compounded either annually or just some sort of compound interest like monthly or quarterly, these ones will always specifically tell you that it's compounded continuously. And so when I plug in those numbers, everything still represents the same value as far as what P stands for and R stands for and T stands for. We just get to use E as our base instead. So let's plug in our numbers that this gives me. It's telling me I initially invest $3,000, so I'm going to plug that in for P. E is not a variable that we're seeking out. Neither one of these things are going to be E. E is the number roughly 2.7, so that is not an unknown. E is a number. The only other unknowns I have are R, which is going to be this right here, and remember this is as a decimal, so let's convert this to a decimal just right off the bat, which is 0.045, and I want to know how much money would be in my account after 5 years, so my T is going to be 5. So let's take a second and plug these numbers into my formula and use your calculator and figure out what number you get. And remember that we are rounding to 2 decimal places, even though it doesn't tell me that because I'm working with dollars. So here's what my formula looks like once I plug in all those numbers. And when I calculate this on my calculator, I am getting about 3,756.97 if I'm rounding correctly to 2 decimal places. And so that's what it looks like to plug in something for compound continuous. We get to use our beautiful formula of PERT, which is usually pretty simple. All right, that's it for today, you guys. That's a review. Actually, as far as sections in your book, that's section 6.1 and 6.2. Great job. Keep working on those weekly problems. And again, check into office hours if you guys need extra help. I'm happy to help. And enjoy your week.